Okay, we are all set now. Now the thing is, what we will be doing is we'll be learning how to analyze raw data of NMR to elucidate its structure. Now I have got certain NMR raw data with me. These compounds were synthesized by Ranjan Da, and the analysis was carried out at IIT Guwahati. So let us begin. Now there are two software which I'll be using for doing the analysis. One is Mestrenova, and the other is, as you can see, the Mestrenova software interface is on the screen, and the other is ACD NMR Spectrum Editor. Okay, it's a academic version that I'm using, so that also can be used for analyzing the spectra. Now, first let me save the unsaved work. Okay, 13C, save, done. So we are done saving. So let us begin now. Okay. So these are the compounds which Ranjanda had sent for the analysis. Okay, DAL, PM2, PQ, PQM, etc. And the structure of the compounds have also been provided by Ranjanda. So let us start off with DAL. See, DAL, it's a dialdehyde having a propane linker between two hydroxyphenyl aldehydic moieties. Would it be hydroxyphenyl aldehydic? No, between two benzaldehyde moieties. Anyways, so let us begin. So for the first step to elucidate the NMR would be to take the FID file. FID is the free induction decay. So you can see the free induction decay file. You take the FID file and you drag and drop it to the ACD NMR spectrum window. Okay, as you can see, some blackish thing is visible here. Now go to interactive FT and then click on it and then click on the OK button. Now see, this is a problem. Okay, proton NMR is not supposed to develop like this. So basically, there is some problem with the proton NMR spectral file or the software that I'm using. So we'll have to go for a alternate route to assess the proton NMR. Now I am not very well conversant with Mestronova, so that's why I do not use Mestronova. And I'm well conversant with the ACD proton NMR software. So what I will do is, let us go to Mestronova first. Now we'll do the drag and drop thing again. We'll drag the FID file of the compound with codename DAL1H into the Mestronova user interface. On doing so, you see the spectrum has developed and some spectra is visible. Now what will we do is we'll go to the save as option. Is there anybody else who is so we'll go to the save as option and we will save the file as galactic.spc file. Okay, galactic.spc file. And since it is the compound is named as DL-1H, so let me put the code name as DL-1H. Okay, so let us save it as galactic SPC file. Now what we'll do is open that galactic file DL1H. There the galactic file is there, and we will drag and drop it to the ACD NMR processor window. Okay, so see, the spectra which was not opening earlier can be opened earlier or open now easily. Now The first thing that we need to do is we have to go for some baseline correction. Okay, so here in the shortcuts menu, you will find various shortcuts like interactive FT phase correction, baseline correction, peak fitting, integration, reference, annotation, multiplex assignments, and many other things. So we'll go for baseline correction. We'll set it to auto mode, and then click on the accept changes button. Okay, so our baseline correction is done. Now we this spectra has developed pretty clearly, and I don't think so we have to do any nitty gritty with it. So what we'll do is we'll go for a peak by peak leveling. For that purpose, you click on that peak picking shortcut button and go for a peak by peak leveling. Okay. Once the peak by peak leveling is selected, it will be highlighted in this yellowish orangish thing. So then you can mark the individual peaks as per your requirement. Now see, some of the peaks do not look like a singlet to me. It seems that these peaks have got various other multiplicities. So what we will do is we will expand those peaks in order to understand the multiplicities better. Okay, so let us expand those peaks. See here. So on expansion, we have obtained these peaks. So let us mark these peaks, and we have a peak at 7.26. 7.26 most probably, if we assess the spectrum parameters, let's see where did it go. View spectrum parameters. So there, this thing will be mentioned. The solvent is a the solvent that has been used for NMR acquisition is chloroform D. So basically, the 7.26 peak that is here might be because of the solvent. Okay, not might be, actually it is actually the solvent peak. There are certain variations of it. Sometimes it is also seen into 7.29, and some discrepancy in the peak position is observed. So that is not our concern here. So let us mark the other peaks. So we have two doublets at 7.01 and 7.03. So since we have marked that already, we'll zoom out again, and then will zoom into the next set of multiplets. See, between 4.5 and 2.5, we have we have a 1, 2, 3, 4, 5 pentet, and we'll have to zoom it in further. Anyways, let us mark the pentet first. So we'll go for peak by peak leveling, and there it is marked properly. And let us zoom in on this particular peak now. So it's a triplet. Okay, so let us finish marking that. So once again we shall zoom out and see if any peak has been left out. No, nothing seems to have been left out. So let us mark this peak at 0.00, which obviously is because of TMS, the NMR reference standard. 1.65, most probably it might be because of the grease or any other factors, impurities that have been used while isolating the compound. Impurities which are tough to remove actually. The compound is fairly pure, so let us see whether the spectra that we are seeing in front of us conforms to the structure of the compound. So first of all, let me zoom in on this. No, okay. Let me zoom in on this particular region, and let me copy the spectra to clipboard. Once it is copied to the clipboard, we'll go to a Word document and paste the spectra. Okay, enlarge it, and there you have your spectral data. Insert a page break so that we can also copy in the expansion. Okay, now let us expand it again. We'll expand it uh, 8 between 6.5 and 8.5. Okay, so there clearly the two doublets are visible. So once again, you copy the spectrum to clipboard and use the paste function to get the spectral data on the Word file interface. Okay, so we have zoomed it in. Once again, insert another page break. Now zoom out again, and now we shall concentrate on the peaks between 5.0 and 2.0. Let me expand it between 5.0 and 1.5. Okay, it's not very clear, so let me expand it further. Okay, okay, that's better now. The pentet is clear, the triplet is clear. So this is enough for our representation. So I've copied it, and once again I'll go to the Word file and I'll be pasting it here. Once this is done, we have our spectral file uh, analyzed. So you can export the report as a PDF from the Word file. So I'll save this as a PDF file in the folder concerned. So DAL1H. So let me name it as DAL-1H. Okay, and let me save it as a PDF file. So now, okay, there's a slight of a problem. Okay, one page somehow it remained extra. The page break came into the wrong page. Why wouldn't it go? Okay, fine. Now that's better. So I'll save it again. Uh, uh, uh. So I'll save it in PDF format. So there we'll replace the existing file. Okay. So we have our PDF data now of which compound? This particular compound. Let me expand it out for better representation. Now see here, in this particular compound, what are we expecting? If we go for theoretical or NMR analysis of whatever we have learned, see there is an aldehydic proton here, there are phenylic protons here, or protons attached to the benzene ring. There is a aliphatic chain of carbon atoms, a propyl chain, and there is an aldehyde here. Okay, so it's a dialdehyde system. So first of all, we can expect an aldehydic peak at around 10 or 9.8 or 10 ppm. Now, since there are two aldehydic group, the aldehydic peak is expected to be intense. So let us go back to the spectral file. Uh, so I'll zoom out again. Look here. At 9.88, we have a singlet. So this particular peak at 9.88, it corresponds to the aldehydic peak. Okay. Now for the rest of it, look at the two benzene rings. So there are four protons here, and considering the symmetrical nature of the molecule, we can expect two doublets from the four protons. So let us check in the aromatic region. Here we have two doublets, one at 7.01 and the other one is at 7.84. So this might correspond to the two doublets. For the protons attached to the benzene ring, and as far as the propyl chain is concerned, consider this proton which is in the middle. Okay, this set of protons which is in the middle. Let me take it to can draw. Okay, so what I'll do is, let me mark the protons. So that way things will be more clear. Okay, so we have a proton here, we have protons here, we have protons here. Let me finish first and then I'll address your queries. It's better, instead of representing this as in this manner, let me write it down in this manner. Okay, so there is a CH2, there is a CH2 moiety here, and another CH2 moiety here. Now have a look at the structure. Let me make it bigger. Object settings. And let me change the size of the, okay, color other. Okay, we're done. Now look here. So let us mark the different set of protons. Let me start off with the aldehydic one. So let me mark the aldehydic ones. So these two here will be our HA, and they will give peak position, NMR peak at the same position because these two protons are similar. Let me mark this proton as HB. So this two is gonna be a HB, B again, HB. Okay. So let me take the A's and B's as subscript so that there is no confusion. Everyone is requested to keep their microphone silent. I do not want any disturbances, please. Any queries you will have will be answered at the end of the session, not now. So let me mark these protons as HC, 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 HC. Okay, so there you go. See, this is only for structural elucidation and to see whether the NMR spectra that we have developed is correct or not. Okay, now look here, the protons are respectively marked. Then let me label it as HCHD. Let me put it up as superscript. Let it be. This portion will be understandable. Now look here, the HA, the aldehydic proton, in this particular case gives an aldehydic peak at 9.88, and that way we can say the aldehydic group is still intact and the dialdehyde has formed. The peak is pretty intense. Also look now, in the aromatic region there are two peaks having two doublets at 7.01 and 7.83. So in order to make sure that the doublets are belong to the protons arising from the benzene ring, let us go for calculation of J values or J coupler. Uh, Sorry, let us go for integration now. Okay, let us go for J coupler. So you can see this multiplet here has a J value of 7.86, and this multiple here has a J value of, sorry, not 7.86, J value of 8.6. Okay, please ignore the hydrogen number here because I have not specified any reference peak based on which the proton count can be shown here. So the thing is, these two peak belong to the protons attached to the benzene ring. Now, considering the downshift of the peaks from the TMS signal, and considering the structure that we have at hand, we can easily say that the HB protons will be more deshielded than the HC protons. As such, we can expect that the peak at 7.01 is due to the Hc protons, and the peak at 7.8 most likely is because of the Hb protons. Okay. Now, having settled that, let us concentrate on the alkyl chain here. So once again, we will zoom out and we will rather concentrate on the aliphatic region. So we have a triplet and a multiplet here. I'll consider that as a multiplet. So see, there are two protons here in the carbon atom, which is in the middle of the propyl chain. So these two protons will split the other two protons into triplets, and it is very apparent that a triplet is there at 4.27. Okay. Also, the four protons here will split the two protons in the middle into a multiplet, which again is visible at 2.34. So as such, the spectra that has been developed confirms the structure of the compound. So that's how we can analyze the NMR spectra of a compound from raw data. There are other nitty-gritties involved like integration and proton counts and other. So I'm not going into that right now. We will stop at this particular stage now.